Welcome, we're going to be doing Physics 123, lab number 5. This is Brewster's angle, and we're going to be reflecting some laser light off of a couple different materials, and then examining at the angle at which we get the special thing happening of one of the polarizations of light not reflecting. So this is the equipment that we're going to be using for the lab. We have a power supply that is just plugged into an outlet, and it's powering this red laser. This is just a continuous laser beam coming out here, and then it's traveling across, and we can see it on the other end of the apparatus. And so what we're going to do is we have two samples here. One is zirconium. It's this square here, and it's mounted inside an aluminum holder. And the other is glass, and we can pull back on these levers and then just insert them into our holder. And so now what we can do is we can adjust the angle here that the sample is positioned at, and that's going to cause the laser to come in and reflect. And we can see it here. This is the reflected beam. For the glass, part of it is also going to transmit, and we can see this spot here. And so the thing that we're going to want to do is we're going to want to adjust this spindle and insert this polarizer. This polarizer is cutting out all the perpendicular component, it's cutting out the parallel component of the light, so that any light that goes through this, we're only looking at the perpendicular component. And the reason we're doing this is because at a certain angle called Brewster's angle, the perpendicular polarized reflection of the light is going to go to 0. And so when this dot disappears, we know we're at Brewster's angle. So what we're going to do, and we'll need to turn off the lights to do this, but we're going to turn the spindle here and observe this laser until it disappears. And then at that angle, that is the angle of incidence of the light that is known as Brewster's angle, where the perpendicular component is gone. It's disappeared. And so if we think about the lasers and what is happening to the light, it's coming in here, and then it's reflecting off. Law of reflection, the incident angle and the reflected angle have to be the same. It's coming in and then reflecting off and going that way to the polarizer, to the screen, and then part of it is just going to go ahead and transmit to the other side. It's just going through, it's refracting through the glass and then bending again, so it's at the same angle as it incident. It's going to come out the same angle that it went in at. And one thing to note, as we change the spindle, we're changing the incident angle, and that's changing this angle by double. So this light is changing twice as fast, the reflected light is changing twice as fast as we're changing the spindle. So when we're at 90 degrees on the spindle, it's going straight through. And then when we're at 0 degrees, it would reflect straight back. So a 180 degree change in the reflected light corresponds to a 90 degree change in the incident angle. And so if you think about that real quick, why that would be, if we have light coming in, why we only need to change the incident angle by 90 degrees to get a 180 degree change in the reflection. But that is an important thing to note. Another important thing to note when we're trying to find the Brewster's angle is that the light is incident. The incident angle we define as the perpendicular of the sample, the angle from the perpendicular to where the light is coming in. So right now, if the light's coming in this way, no fingers, I'll do this. The light's coming in this way, this angle is Brewster's angle, right? And so this is what our spindle is measuring. It's at 0 degrees, and it's going to 55 or whatever the case may be. If I change this, this is an incident angle of 90 degrees, and as we put it in, we get an incident angle of 0 degrees. And so once we find this measurement, that measurement itself is Brewster's angle. Okay, so we have the glass inserted in here, and we're going to go ahead and just do a sweep through all the angles just to see how the laser responds. So I'm just rotating the spindle, so you can see it's going in this way. As I do that, we see the beam come, and we see it cuts out around this angle. We're a little bit less than 60, and then it comes back in right here. So we saw it reappear. So it just cut out. Then if we come all the way we see it's still as strong. So if we just watch this, I'm going to go back. I'm going to turn it back to how it was. We just see it go along. We see it cut out for a section, then we come in strong again. And so in order to find a good accurate measurement, we know it's in the ballpark of maybe 55 to 60 degrees. But in order to get an accurate degree measurements, we're going to go ahead and flip off the light so it's easier to see exactly when it goes completely black there, and then find Brewster's angle that way. So let's go ahead and turn off the light. Okay, we've turned off the lights. We still have the glass in the sample, and I'm just slowly adjusting the angle until we see the beam totally disappear. So you may not be able to see it on the camera right now, but it's still very faint to the naked eye. I'm gonna just try to find exactly where it disappears. And it looks like right there. So it's completely gone. In the room, if I look even super close, it's completely vanished. And so that's a good sign. That means we are exactly at Brewster's angle. And now we can go ahead and record that angle. Again, this is the incident light angle as it's coming in here. This is the perpendicular for the sample. So it's coming in at 0 degrees. That is Brewster's angle right there. So you can use that to find the index of refraction of glass. And that's all the data for our first sample here. Okay, so now that we have the Brewster's angle for glass, we're going to take this zirconium sample and just take out the glass and put it in here. Now, one thing that is different with the zirconium is that it's mounted in this aluminum, and so one thing you'll notice is that we don't have the transmitted beam that we did with the glass. If we had a zirconium sample this big that we could just put in like the glass, we would still see the same effect, but we had to, to protect the sample, we put it in this aluminum casing, which is why we don't have the beam showing up there when we're at an angle. But let's go ahead and do the same procedure here. I'm starting at 90 degrees. We see the reflected beam here, and then I'm going to go ahead and turn it, and we saw it disappear. So this is a little bit greater than the glass. We're around 65 degrees. If we keep going, we'll see it reappear over here. And so I'm going to go ahead and sweep back through. We're starting here, moving the spindle, increasing the incident angle. See it disappear and come back in. And so let's go ahead and turn off the light to find exactly where it disappeared in this range between 65 and 70 degrees. We've now turned off the lights, and we still have the zirconium in there. And I'm just going to do the same thing with the glass. I'm slowly adjusting the angle until that dot completely disappears. Okay, that might be it. I'm going to go just a little bit further, and we see it reappear right there. So I'm going to go back to where it was completely dark. Just want to make sure that I'm at the right angle. Okay, that looks like it. So it's completely gone here. And this is the Brewster's angle for the zirconium.